Welcome everyone to today's version of the Inverse Problems International Seminars. So we're happy today to have Matteo, Santacesaria. Sorry, I may not have pronounced it absolutely correctly, but nevertheless, we're happy to hear about the stability for nonlinear inverse problems from finite measurements to manifold learning. Thank you so much, Matteo, for giving a talk.
Thanks a lot, Knut and Katja, for the invitation for this nice seminar series. So it's a pleasure to be here. And so I'm gonna talk about let's say a series of results that we have been working on in the last few years. So some are not very recent, but I will try to show some more recent results at the end. So let's say the main topic, as in the title was written, is nonlinear inverse problems. So just to give you a bit of the notation I will follow during the talk, we are considering inverse problems of this form, where we have a nonlinear forward map F and some unknown X we want to recover, and we have some noisy measurements Y. And so in general, we will consider general map between Banach spaces. And of course, with this framework, we can model very general inverse problems in medical imaging and other applications. Well, let's say that the prototypical problem I have in mind is EIT. So where we want to recover a conductivity distribution in a, for example, for medical imaging applications. For example, this is lungs. From some indirect measurements given by electrodes and voltage measurement taken on the boundary of the physical body, for example. And I will tell you more about that. This is a classical example of nonlinear inverse problem. And so in this talk, I will address two main gaps in let's say in this theory of nonlinear inverse problems. So the first one, let's say, is the gap between, let's say, infinite dimensional setting and finite dimensional, let's say, real world measurements. In practice, it's very natural to model inverse problems, for example, for PDEs in an infinite dimensional setting where you have both the input and output elements of some function space. And there is a huge theory on this, showing uniqueness, stability, etc., or some theoretical reconstruction algorithm. But then in practice, where you want to solve this problem, we only have access to a finite amount of measurements that we could model, for example, with a projection operator, or let's say a discretization operator of your applied to your data Y. And in practice, yeah. So and there is let's say, it's hard to translate, let's say, the nice theoretical results in the infinite dimensional setting to the finite dimensional, let's say, more practical one. This is what I'm talking later. Another gap is the one between well-posed problem and ill-posed one. So it's well known that, let's say, for example, inverse boundary value problem for PDEs, for example, the Calderon problem, or for EIT, are severely imposed. So even though, so you can prove uniqueness and some kind of stability, still the stability of the reconstruction is very, very weak. And this can be seen in these classical results of logarithmic type stability estimate, where somehow that translate in quite, let's say, not high resolution reconstruction. These are some example from old work with collaborators, where in case we want to recover a piecewise constant conductivity, and without assuming so much on that, we get a reconstruction which is very blurry. And somehow the holy grail of having a nice reconstruction algorithm is Lipschitz type stability estimate. So this would be Lipschitz property of the reconstruction operator. And this can be done also for EIT, but we have to pay some price. And this is also some reconstruction that we obtained in some older work. And you can see that somehow if you restrict the reconstruction, the class of your unknown in a specific, let's say, setting, you can recover some sharp jumps, for example. And so how do we solve these gaps? And that is the main content of this talk, is to, let's say, introduce some prior information on your unknown. So of course, in the case where we work in the infinite dimensional setting, we need infinite amount of measurements to recover your unknown. But as soon as you restrict yourself to having only a finite amount of measurements, then you need to put some strong prior on your unknown. So, for instance, to assume that you are not belong to some finite dimensional object in your function space. It can be infinite dimensional. And the content of this talk is the following. So we'll consider some kind of priors to the unknown in order to recover some classical uniqueness and stability results. So first I will consider like linear priors. So we assume that we are reconstructing on a finite dimensional linear subspace. And later about some extension in the case of finite dimensional manifolds. And then I will jump to a different point of view where we don't know what is this manifold of your unknown, but we want to, let's say, learn it using machine learning techniques, specifically generative models. And I will talk about some, let's say, some connection with how generative models can be used with inverse problems. And so, so there will be some kind of a jump in the middle of the presentation going to machine learning. And so this is the main outline. So actually, I will start with basically one of the first results we obtain in this setting, which is specifically for the Calderon problem. Then I will explain some extension for general nonlinear inverse problems. And then later, yeah, I will talk a bit about how machine learning can be useful for modeling the priors. And then we have some very recent results on diffusion models that somehow is not yet applied to inverse problem, but it's very, very promising. Okay, so I wanted to talk a bit more, to spend a few slides on these results of the Calderon problem, which is already not so recent, but I think it's always nice to mention it because it's I don't know, I think it gave a lot of motivation to do what we did afterwards. So so we consider the classical Calderon problem here. Okay, I put dimension d greater than 2, but in practice our results works only in three dimensional higher. So we consider a bounded domain and with a conductivity distribution, general can be an infinity function bounded with a positive constant from below. So the physical model is the conductivity equation in the domain with some where we impose some Dirichlet condition, and the forward operator is called the Dirichlet tonal map that takes as input the Dirichlet value of this this problem F and associates the normal derivative of the unique solution of this Dirichlet problem restricted to the boundary of our domain. And this is a nice interpretation that these models, it's a kind of idealized model of boundary current and voltage measurements for a conductive body with conductivity sigma. And the classical Calderon problem asks if it is possible to recover this unknown function sigma on the whole domain from the knowledge of this boundary operator, which somehow represent all possible pairs of current and voltage measurements of the boundary. And so this is an inverse coefficient problem. We want to recover the coefficient of this PDE. So, I mean, I'm just gonna restrict directly in a specific setting. So first of all, I will, the usual way to resolve this problem is to do a change of variable and reduce to a different equation where the perturbation is not anymore on the higher order term, but on the zeroth order term. So we have this kind of stationary Schrödinger equation with where now the unknown is a potential Q, and we can still define the Dirichlet-Neumann map associated to this Schrödinger equation, and then there is some equivalent, some way to go back and forth from the Schrödinger equation to the conductivity equation, but this is somehow easier to study. And the main thing I want to mention, and I'm terrible here, I'm not citing all the plethora of works in the classical setting. I'm just saying that most of the results for this problem are in the infinite-dimensional scenario, where we know the full Dirichlet-Neumann map, and then we want to recover a potential Q or a conductivity sigma. But now let's put ourselves in a more realistic setting. I mean, it's still idealized in many ways, but it's already slightly more realistic. So we consider that we have access only to a finite amount of pairs of voltage input and current, let's say output, so measurement given by the Dirichlet-Neumann map applied to the specific voltage. And then we want to recover our unknown potential Q just from this finite amount of measurements. Of course, they are still continuous objects, but anyway, still much less than the full map. And of course, this is impossible if we don't impose any prior information. So the prior assumption that we put on this unknown Q is the following. So assume that Q belongs to this space WR, which is basically the intersection of a known finite-dimensional linear subspace with a ball in the L-infinity norm of some radius R, which is known. And then of course we need this condition on the Dirichlet eigenvalue of the Schrödinger operator in order to have the Dirichlet-Neumann map well defined and that the problem is uniquely solvable. So basically, it's apart from this condition on the eigenvalue or on this a priori bound on the L-infinity norm, we are basically assuming that Q belongs to a finite-dimensional subspace of L-infinity. And in this setting, we got this result that says as follows, so if we are in dimension 3 or higher, this in collaboration with my colleague Giovanni Alberti, and so we assume that we have this domain W, this is a finite-dimensional subspace. So we show that there exists a capital N with this following property, and that if we fix some reference, let's say if we fix a potential Q1 in this space, then we can construct N boundary voltages, so boundary Dirichlet values, such that we can somehow test for any other potential in the same space WR, that if the Dirichlet map coincide on this of these two potential coincide on this set of boundary maps, then the potential coincides. So this is a uniqueness result, testing only with a finite amount of boundary Dirichlet values. And then also these can be extended this in the Calderon problem, of course, adding some regularity assumption so that we can do the change of variable to the Schrödinger equation. And then, so yeah, this, I mean, the idea, somehow, I think it's not so complicated to explain, so I wanted to just spend one slide on a sketch of the proof. So the idea is that is as follows. So we have somehow so the main construction is based on let's say on this family of solution called the complex geometrical optic solution, and let's say the main bulk of the technicality was the study of this special solution was done in the seminal paper by Sylvester and Ullman. but the idea is to see this construction in a slightly different way. So we basically we consider this nonlinear operator U, which is somehow a nonlinear Fourier transform of our unknown potential Q, and this R term is this let's say a remainder term from this complex geometrical optic solution, and so we can write this operator as a Fourier transform plus some nonlinear term. And the interesting thing is that, okay, assuming that this let's say the Dirichlet map coincides on this finite amount of properly chosen boundary values, that actually let's say we have to choose them that in a specific way that they are exactly like the boundary values of some complex geometrical optic solution for this Q1 potential. Then using what is called Alessandrini's identity, which is some kind of integration by part, you can transfer the information on the identity on the boundary, on the identity, integral identity on the inside of the domain, which so it tells you basically that we have this quantity. So this is a sequence depending on some natural number L of this nonlinear Fourier transform. So we know that somehow the first n say elements of this frequency of this sequence coincide, and then the thing is that if we choose these boundary values well enough, we can prove that this nonlinear term is a contraction. And then we just do this simple trick. So we basically we consider the L2 norm of the difference of these two potential. So by Parseval, the norm is the same of the Fourier transform of this difference. So we can then decompose. We can just write F as U minus B, and then we're using the fact that the first n term of the sequence of U coincide, we can rewrite in this way, and so we have a linear term, or we have the projection on, let's say, on the high frequency of the Fourier transform of this difference, and then we have this nonlinear term, but if we choose let's say these boundary values well enough, we can prove that this is a contraction, and so we get this 1/2 term of the same quantity we had at the beginning. And now, how to get rid of this term here? We just remember that we have that this Q1 and Q2 belong to a finite dimensional subspace, so we can add this projection. So this finite rank operator for free inside this equation, and now we get if n is taken sufficiently large, we can prove that the operator norm of this composition is small enough, and because of this projection will converge to zero in the strong operator topology, and so basically this will get. This gives us that Q1 needs to be equal to Q2. So somehow the nice trick here is just to exploit this finite dimensional projection and then taking n sufficiently large to get this uniqueness result. Then of course this we can be relaxed, and we can get a Lipschitz type stability estimate in this same setting. So we can get also some explicit constants that are very bad, but this is kind of coherent with the ill-posedness of the problem. So here n is still connected to the number of boundary measurements we have taken, and so yeah, somehow it's nice to have Lipschitz stability, but still we have this very bad constant. And this is somehow somehow new, because most Lipschitz type stability estimates for this problem were obtained where on the right hand side we have the full Dirichlet map. So this was what was known at the time, and so it's kind of original part of this stability. And afterwards, there was an extension of this work by Bastian Harrak, who extended this kind of stability and uniqueness in a more realistic setting of the complete electrode model, which is a more realistic model for electrical impedance tomography. And then afterwards, somehow we were able to extend this to general, let's say, nonlinear inverse problems. And so we couldn't use anymore this CGO construction or the specific techniques of the Calderon problem. So the idea is the following. So we consider still two Banach spaces and some polar map between X and Y. And then we still consider a finite-dimensional subspace of our input space X. And then we consider now just a compact subset of this finite-dimensional space. And so there is this very, let's say, classical result. This was already known, that it is basically a kind of inverse function theorem in Banach spaces. So the idea is that you have a C1 operator between two Banach spaces that is injective on this finite-dimensional space, and also the Frechet derivative is injective. Then it's possible to prove a Lipschitz type stability estimate for points in this compact subset of this finite-dimensional space. And here this Lipschitz constant depends somehow on some kind of lower bound on the norm of the Frechet derivative. And somehow based on this idea, there were a lot of stability, Lipschitz type stability estimates for EIT or for other nonlinear inverse problems by a lot of colleagues. And but if you look at these results, it's somehow not really satisfying in the sense that you know that X1 and X2 belong to a finite-dimensional subspace, so they depend on a finite amount of parameters. But on the right-hand side, you have an infinite-dimensional object because you have f of, so you have this element is f of x1, f of x2. They are elements of y, so they are infinite-dimensional objects. So our question is, can we do better? Can we just get a similar type of estimate, throwing away most of the measurements? And basically the answer is yes. And so to do that, we have these results where we in the same setting. We assume somehow that someone else already proved a Lipschitz type stability estimate, and now we consider a sequence, so a operator Qn that somehow model a discretization of our measurements. So it's somehow you can see this is a projection operator on Y, on the space of measurements. And then we can prove that if we take n sufficiently larger, and this n can depend explicitly on our prior assumption on our node, so on our linear finite-dimensional space W, and also on the Frechet derivative of the forward map, then we can basically get the same Lipschitz stability estimate, only paying a small price, having a slightly higher constant. And but now we only need n, let's say capital N measurement, and not anymore the full measurement on the space Y. And somehow, I mean, the techniques of the proof are more like classical functional analysis, but still we have to exploit some, let's say, properties of finite rank operators. And so this was for linear priors, and then later we were able to extend this to nonlinear priors. So I'm just giving a very short summary of what we got. So this setting is still nonlinear inverse problem between Banach spaces, but now we assume that our unknown belongs to a finite-dimensional manifold with some regularity properties. We assume that the C1 manifold. and still we assume that we have a compact set in this manifold. And now we still have some inductivity properties of F, and now the differential of F. And then we can still prove that we can get a Lipschitz type stability estimate with a finite amount of measurements on the right-hand side. And okay, so this is where the main, say, stability result we got in this setting. And we applied it for some, for the, let's say, for the Calderon problem in some specific setting where we have nonlinear prior on our known, and also to other nonlinear inverse problems. And but then, yeah, so the follow-up question is that this manifold, of course, in order to prove these theorems, we have to know it, we have to have some regularity assumption, but in practice, it's hard to model your unknown quantities with a manifold like that you can describe analytically. And so what is the idea? The idea is that we could, if we know like a certain amount of examples of unknown that we want to recover, we could try to use machine learning to learn and have an approximation of our manifold. And so in one way to see this is that we would like to construct the call generator from some new space Z that I will call a latent space, or as it's called in machine learning often. So this dimension of the space Z will be approximately the dimension of the manifold. And then we hope that our manifold of interest is approximately the range of this generator. And somehow this would hopefully, let's say, reduce even more the degrees of freedom. So you would get better stability estimate and more accurate modeling in more realistic setting, and hopefully even less computation. And so this is what we tried to do. And but let's see how we would solve an inverse problem if we were given this kind of generator. So a classical way of solving the inverse problem is using regularization theory. So we have so we want to recover your unknown x, solving an optimization problem. So this is a classical econ of regularization, where you have a data fidelity term and a regularization term. And this is like, but of course, this R term must be somehow designed ad hoc. And if we have available a generative model, so this map G, then we would not do anymore the optimization on the original input space X, but on this lower dimensional latent space Z. And so there will be some kind of constrained optimization where we look for the best, say, Z that would satisfy this data fidelity constraint. This is one option. Of course, then you can add more regularization term. And then at the end, when you find a minimizer of this optimization problem, you just plug it back to your generator G, and you get some approximate solution. And this is connected to theory is called compress sensing with generative models, and this was studied also in this setting. And but let's see some example of how this works, for example, for nonlinear inverse problems like EIT. So there was this paper from 2019 where they used this kind of approach for EIT, and these are some quite nice, say, reconstruction results where we see that I mean, at least in this setting, having a generative model gives much better reconstruction compared to the classical, let's say, Tikhonov least square method. Okay, but there is a problem here that in order to fit, let's say, let's say, this generative model in our theory of inverse problem between Banach spaces, we need somehow a generator that would output, let's say, continuous object. And this is what we came up a few years ago, because most of the machine learning, let's say, literature and theory is done in a finite dimensional setting. And so since we wanted then to try to prove some I don't know, stability results for inverse problem, we needed an architecture for machine learning, so a generator, so a map that would output, that would generate infinite dimensional signals. And so we came up with this this construction, which we call continuous generative neural networks. And this is just an example. So you can think this as a map from a very low dimensional space, for example, to a space of, let's say, idealized continuous images, so the L2 of this square. And then if you train this model on, for example, a dataset of handwritten digits, this classical MNIST dataset, what you would do is that when you sample some vector in your input 40-dimensional space, you would hopefully generate not just Gaussian images, but something that is meaningful, in this case, handwritten, something that resembles to your original dataset. So, for example, this handwritten digit. And here is just example of 16 generations of this generator. And so in practice, of course, if you want to do this for medical imaging, you would generate, I don't know, MRI images of the brain or of the lungs or whatever you have in mind. So, of course, this requires a dataset of clean images, which is often not available, but is a different issue. Okay, so how we did that? So, okay, maybe I will go a bit fast, but we started from some famous, some popular architecture. So here we started with, so in general, neural networks are composition of linear layers and nonlinearities. And so we wanted to mimic, let's say, this structure. And the idea we took was to start from a popular architecture, at least at the time. So it was convolutional neural network, where the linear part is modeled by a convolution, and basically the closest thing we were able to find was to use wavelets. And so we somehow the idea is that our architecture starts from a finite dimensional space, but then it embeds immediately in some scale space of a wavelet multi-resolution analysis. And here, I'm sorry, I will not go into detail, but somehow the idea is that we replace let's say the resolution of in this discrete generator. Normally, the resolution of the images will change at each layer, and here what will change is the scale of the wavelets. So somehow the resolution will increase more and more. And so one of the motivations to having this architecture is that you are able to output continuous signals. So you have something which is called discretization invariant, so that at the end you can somehow evaluate your signal without a grid or without a mesh. So. And but then also we wanted to show that it would be useful to solve inverse problems. So we somehow characterized the architecture that were injective using this compositional structure and the wavelet. And then later we just somehow combined these injectivity results with the previous stability results for manifold. And so we get this Lipschitz style stability estimate for inverse problems, where now the unknown belongs to a finite, to a compact subset of this manifold, which is now let's say the range of this generative model. And then we apply this. Actually, in this paper, we didn't apply it to nonlinear inverse problems such as DIT. This is just some example on deep learning. And so here, for example, we have that our unknown is this yellow curve, and these and the measurements are like this. In the noisy case, is this blue, very rough curve. And then we have some reconstruction at each rows using different like wavelet bases. And then we have some normalized mean square error here in these numbers. So anyway, so we basically the bottom line of this work was that somehow this approach works well for very smooth signals, but it was not really working well for non-smooth signals. That's something that we are working still now with other ideas. But anyway, there is another limitation here, is that somehow this is a very simple manifold from a topological point of view, because we only have one map. So we cannot model complicated topologies. So for example, if we had a manifold which is given by these two circles, in using just one map would give a very bad approximation. And so what we did, we extended this to allow for multiple charts. And this is something we did later. Okay, this is probably even more technical, but the idea was somehow to combine several generator together. And the technique we used was something which is called the variational autoencoders, and also normalizing flow, but this was not the main feature. So the tricky part was here to do the learning in a way that the charts will somehow talk, it will overlap well together. And also we proposed in our work a way to solve inverse problems on this manifold. So also a way to jump from one chart to the other. And this was done also with Giovanni Alberti, but also with Johannes Hertwig and a former PhD student of us in the Asciutto. And here, I mean, this is just some nice example of manifold that we were able to recover. This is in a low dimensional setting. So in the first row, you have like let's say somehow the noisy samples of the manifold we want to recover. On the second row, somehow the generated samples after the training, and you can see the colors that they say they're indicated different charts. And then for the specific setting of the torus, here we're even plotting each individual chart that we are learning. So we are quite happy about this result. And then we applied this just about learning the manifold. Then we used it to solve inverse problems. And okay, we did also other example here. I just want to show one example with EIT. So let me try to explain what's going on here. So in this setting, we have a data set of like conductivities, which is constructed as follows. So we have our domain is the unit square, and we have a fixed background, and we have two circular inclusions with a fixed conductivity. And so the degrees of freedom here are that the center of these two different inclusions and the position, and also the radii, and they cannot overlap. So this creates some non-trivial topology. And so somehow we train our model on this data set, so it's able to generate this kind of conductivities. And then, okay, these three rows are the following, means that in the first row we have some target conductivity that we want to reconstruct. In the second row, we have the reconstruction using just one generator, so something that shouldn't be able to model the complex topology of this manifold. And the second one using two generators, so it will be more expressive. And okay, so you see that okay, they are not great anyway. EIT is a hard problem. So in some case there is one that fails, and other that, for example, in this setting, this one with 2 generators works well. Anyway, in average, we saw that having 2 generators works better. And so we were happy about that. And okay, maybe just a final thing I want to mention on this setting of manifold learning is a very recent work that we uploaded a few weeks ago, which is called Manifold Attracted Diffusion. So here, we still didn't apply it to inverse problem, but the idea is that we have some data, which is so we basically want to learn a manifold, but only from, let's say, corrupted data. And let's say the state of the art right now of generative model is what are called diffusion models. And if we use, let's say, standard diffusion models on a noisy dataset, then it will just generate again noisy images, for example. And so what we did, so the idea, of course, that somehow this generative models, especially diffusion models, works well because somehow the meaningful data belongs to a finite dimension, to a low dimensional manifold Riemann space. This is called the manifold hypothesis. And also we somehow, so we noticed that somehow the noise in most cases is somehow can be seen as a low magnitude variation in somehow in an orthogonal direction to the manifold, and while somehow the richness of the manifold is more like in the tangent direction of the manifold. And with this let's say thinking, we developed, let's say, a modification of these diffusion models that somehow does not require new training. So we can still train on very noisy images or objects. And so we have this new, let's say, modified score. I mean, we have a modification of the way we generate images that somehow projects these noisy quantities to the original manifold, and somehow it acts as denoising. And this is we're quite surprised about this, and I will show just a few pictures to explain how it works in practice. So in this case, we had let's say a training set of synthetic shapes. So these are these kind of funny shapes with smooth shapes with some construct with the background, and we were adding a very large amount of noise. And then we trained a standard diffusion model on these very noisy images, and then our modified one. Sorry, the training was the same, but then the generation was modified by us. And then we see that with a standard generation, we get very noisy images, which are similar to the training one. But with our method, we were able to maybe not recover perfectly because still we have some funny things, but still we recover quite nicely the shape. And this was on synthetic data. But then we were trying this on real data on cryo-electron microscopy. These are extremely noisy data, and that we took on some public available dataset. And then just by tuning well our method, we were able to get this much more, let's say, meaningful reconstruction. These are, of course, they are not like state of the art, but still we were kind of happy to recover some nice meaningful images from these terribly noisy ones. Okay, so let me conclude. And so the main message I want to give with this talk is that somehow using this finite dimensional prior is very helpful for mitigative posedness especially for nonlinear inverse problem, and it also can guide you to how to choose a discretization if you want to, let's say, do reconstruction. also that we can use generative models for modeling these priors very efficiently. And then we have this proposal of this continuous generative neural network that is one way, for there have been many other propositions to construct these generative models in infinite dimensional space, then combine them with inverse problems. Then, of course, we have this, let's say, yes, it would be, our hope was then to use these diffusion models for solving inverse problems. This is something that we can do, but somehow there are a lot of open questions also about, let's say, how stability can be improved using diffusion models, and this is something that we would like to study further. And also another thing we are working on is, let's say, having some continuous generator that would be able to generate discontinuous signal and somehow would, let's say, act between Sobolev spaces, for example. And we hopefully will publish this soon. Okay, this is just a few references of what I talked about, and I thank you for your attention.
Great, Matteo. Thanks so much for a very nice talk. Excellent. So the floor is open for questions. So if you have questions for Matteo, please unmute yourself and ask questions. Yeah, you had Sergio, you have a question? I was wondering a little bit, Matteo, for the last example, the MAD.
No, a mistake. No, because excuse me.
Hello. Okay, it was not a question.
Yeah.
Okay.
Well, I think I had a question. So for this MAD approach, so in some sense, could you think about sort of this stable part as the low frequency part, and you adapt the score function to sort of fit it towards the low frequency part? Or how was actually what's involved in the denoising here?
Yeah, this is a very interesting question. So we don't have an interpretation of these as let's say, low frequency or filter or something like that. So the main thing is that we realize that the standard definition of a score requires that the probability distribution is, let's say, is non-singular. That must be supported everywhere. And so the first thing we did was to define a score that would be defined also for like Dirac deltas, and that's something that and then we realized that this extended score is somehow coincide with the score of a Gaussian distribution with a specific let's say I mean unit variance, and anyway, and then we I know it's so we yeah, I don't know, it's hard to I'm not really sure how to answer this question, sorry. It's but anyway, we found out that if we have let's say a manifold, so a low dimensional manifold in your ambient space, this and then you have your samples which are, let's say, noisy version of this manifold. We were able to, let's say, tweak our parameter to, let's say, push the generation towards let's say, the manifold. And so this is the kind of regularization we see, but we don't have interpretation in the sense of frequency, let's say, of the data. From, I mean, for at least for now, maybe later we will discover something.
Okay, thanks so much. Any other questions for Matteo? Otherwise, thank you so much once again for a very nice talk. Many interesting aspects, Matteo.